Hey, good morning, everybody. I hope that slide is visible to you. So please confirm we'll start right away.
Yes, sir.
Yes.
Thank you. Today we will take off to a new topic. I guess I just mentioned about it earlier. What is referred to as hypersonic equivalence. It's equivalence, that is examining the equivalence between a hypersonic flow problem and another problem for which solution exists. I'll explain these things later, but then I'm just telling you what is the perspective or what's the context of the term equivalence here. Our interest is on solving hypersonic flow field. And we have already seen there are several difficulties in solving them. So we are exploring different options. Now, one of them is to explore to examine the equivalence between a given hypersonic problem and another problem which can be related to it on certain physical grounds. Now, the another problem that I mentioned, that is, let's say problem A is hypersonic, problem B is some other problem which is equivalent to it. Now, problem B is in such a way that we have either experimental or theoretical data available on it. So if I can strike an equivalence between problem A and B, then I can use some of the results which are available for problem B to interpret the physical parameters in problem A. This is what is being attempted here, or this is the core approach in hypersonic equivalence. That is, you try to find out a similar physical situation where experimental or theoretical data is available, and then if it is theoretically feasible to correlate them to an experiment, to a hypersonic case, then we can make use of them for practical applications to get an estimate of, again, the all important parameter, the pressure distribution on the board. So this is the approach of what we are going to describe as hypersonic equivalence. Okay, so we start off with reviewing what we have done so far. In the last few sessions, when we were focusing on similarity and the small perturbations approach. I've just summarized here in the first 2 points as what we have achieved there. We see that we see the statement summarized here of hypersonic similarity flows over a finely related bodies with the same values of gamma and the product m infinity into tau and alpha by tau. Look at them. Gamma, we assume that all properties are the same, or gas properties like gamma are same, and we also have these two similarity parameters, m infinity into tau, the product of them, and alpha by tau, tau is being the inverse of slenderness ratio. So gamma, the product of m infinity and tau, and the ratio alpha by tau, if they are the same for two affinely related bodies, then the values of Cp by tau squared at the corresponding normalized location will be same for each of the or both of them. So we are not saying that the pressure distribution will be the same. We are saying that Cp by tau squared will be same. Cp is a non-dimensional parameter, tau is a non-dimensional parameter. Needless to say, Cp by tau squared is a non-dimensional parameter. So what we are saying is that for these two bodies, the value of Cp by tau squared at the corresponding normalized locations, x by L and y by L, not at x and y. We are saying normalized by, because the scale can be different in one direction. That's why we call them as affinely related. So in the flow direction, the scale may be different. So x by L, y by L. So on those corresponding normalized locations, the Cp by tau squared will have the same value. Now, so once we have Cp by tau squared, then by substituting the corresponding value for tau and v infinity, etc., and we can get the corresponding value for pressure distribution. So this is the approach that we have used in similarity based on similarity arguments. And this is restricted to the assumptions of small perturbation, and that we have seen in viscid flow, and uh, normal or the axial variations are lower as compared to normal variations, etc. And so all that which we carry forward with perturbation, small perturbation analysis, and the bodies have to be invariably slender, and the for leading edge should be slender as well. So you need to have a sharp leading edge, etc. Whereas now what we are trying to do starting from here is we are moving to hypersonic equivalence, which is going to take this further to blunt nosed slender bodies. That is, you will not have an attached shock. The shock will be detached. So you are sort of relieving one assumption, that is the theta is small, the deflection angle. We are now going to see whether we can carry forward the same equations and have some other methods of solution where when you have a blunt nosed slender bodies. Slender, they have to be still, but the nose can be blunt. What do we mean by blunt nose slender bodies? I just have some pictures here. So these are examples. Actually, they have a lot of applications in hypersonic aerodynamics. The blunt nosed slender bodies. You can see in all of these that, and that's the reason why there are a lot of. Actually, I have taken these pictures from different papers. I mean, different experimental studies, numerical studies, etc. So they are all focused on various applications where these features are these geometry features are important. So you can see that the nose is blunt, but the body can be considered slender because it's the length is much higher than the diameter. So all these are examples of this. Is also, I mean, here only the part of the length is shown. It's actually a long body. So this is also a blunt nosed slender body. Similarly, this is an numerical model for a model which has been analyzed using computational modeling for hypersonic flow past it. So these are all, and this also is another experimental model where you have a blunt nose but a long structure for the body. So these are the kind of bodies that we refer to as blunt nosed slender bodies. And the applicability of what we are going to discuss further is going to be restricted to blunt nosed slender bodies. Okay, now I need to have again set of equations and then correlation between them, etc. So as long as we are talking about theoretical formulations, we need to have some basis, or we need to have some starting point from the governing equation. So we have to back and forth refer to this set of equations. Actually, what I'm trying to do here is this slide I'll be showing it later in a later context. But here, all that I'm going to say is that when I initially said that we are going to look at two problems, one for which solution is existing, the other for which is an hypersonic flow problem. So, and then we are trying to strike a balance or examine the balance between the two. This I mentioned already. So what I am trying to present here is two sets of equations. One pertaining to a slender hypersonic body, and the other possibly where a solution exists. And this is going to be the basis for our further discussions, striking an equivalence between the two. Okay. So on your right hand on the screen, this is what we have discussed so far. Steady flow, 3D XYZ plane in an XYZ system, the hypersonic small perturbation equation. So just look at them. These are the ones that we have painfully looked at several times in the previous sessions. Dou rho dash by dou x bar, etc., where all of them are non-dimensionalized, and the velocity components are expressed as perturbation components V dash. V by V infinity, W dash, W by W infinity, etc. So they are all perturbation components and small perturbations. And we have seen the assumptions related to that. And needless to say, the set of equations apply to inviscid flows and steady. You don't have the time in that. Okay, so on one side, you have the steady flow 3D domain. This is where we are seeking. These are for hypersonic flow, and these are applicable only to hypersonic flows. Please remember that. The perturbation equations, the way that we derived them, they are applicable only to hypersonic flow because the perturbations, the variations that we consider or the terms that we neglect are become negligible only when Mach number increases, goes towards infinity, or and the yeah, basically when Mach numbering goes towards infinity, etc. So the perturbation forms the way that we have written are applicable to hypersonic flow. So this is a 3D governing equation for applicable for steady inviscid hypersonic flow, and this is where we are looking for solutions. And on the left hand side, you have probably a more familiar one, unsteady flow in two-dimensional domain. This you have been seeing from the fluid mechanics days. So it's continuity, momentum, and energy equations, again in non-dimensional parameters, but written for unsteady flow. Unsteady flow. You can see that all of them have unsteady terms, right? All of them have dou by dou t. So the first one is for continuity. The other two are for the two components of momentum. We are talking about two dimensions, 2D, y and z. Y and z. X is not there. I'll explain why. So we are considering 2D domain. We are considering the YZ plane, and we are considering the unsteady form of continuity, momentum, and energy equations as applicable to a 2D domain. Particularly a YZ domain, and that's the reason why you have V, W, Y, Z. We don't have U because we are conveniently considering it in the YZ plane, whereas the other one is XYZ. So on the left hand side, you don't have time because it's steady, but you have 3-dimension XYZ. Here you have time, but you don't have X dimension. So X is not there. Okay, so this is 2D transient, and this is 3D steady. 2D transient, 3D steady. And this is where we are trying to explore for equivalence. Now, why are we doing it with so much difficulty? Because for the 2D unsteady relations, there are some solutions. Some for physics which resemble this kind of motion, there are some results and there are some experimental values, some theoretical formulations available. And if we have an equivalence between the two, we can probably interpret the hypersonic flow problem using the unsteady results of 2D domain. I pause here, though I know that I'm not told much in terms of what we are actually doing. I just introduced some basic things which we are going to further explore. But if you have any, from what I said so far, if you want to ask something or if you want to clarify something, I can do it right away before we proceed further. So I wait for your questions if there is any. Okay, and yeah, I know that it's too early to have questions because we have not even started the analysis yet. But then we'll carry forward. We'll continue. Just look at the two sets of equations. I want you to observe that there is some kind of similarity between them. A similarity in the sense, except for the presence of transient term in the left hand. Here, if you look, say for example, if I just take the first set, the continuity equation, I don't have X in the right hand, but I have T. Rho by dot T is there. Here I have dou rho by dou x. Now, what happens after that? Here I have dou rho v, of course, the non-dimensionalized form. Rho v by dou y. Here I have dou rho v dash, the perturbation component by y. Similarly, for the w term, dou rho w by dou z on the left-hand side, dou rho w dash, the perturbed 3D velocity by dou z. So there is some similarity in the terms. Even the first term differs only in on the right hand side, it's in the spatial coordinate. In the left hand side, it is in the time-wise coordinate, the temporal coordinate. Similarly, in other equations also, you have rho v by rho t here. Similarly, here you have the additional term rho dou u by dou x. U by x, because we are considering the x component. Here on the left hand side, it is v and t, because we are considering in the yz plane. We don't have x component at all. Okay, so if you go like this, you can see that there is a mathematically, okay, physically there are two different things, but mathematically in the constituents, in the composition of the equations, there is a similarity. There is a 1-to-1 in a somewhat loose terminology. I can say that there is a 1-to-1 correspondence between the mathematical terms. So there is some mathematical similarity between these equations, which means that if I have solution for them, one of them, then I can try to correlate it to what happens in the other system. This I'm just stating it now. We'll try to understand this more physically in the coming discussion. Okay. So this is what we are trying. That is unsteady flow in 2D domain where there are some results, some experimental data, some numerical results, etc. And what we have, our problem is in the 3D domain, hypersonic flow, where we have a similar set of equations. So we are trying to see whether some of these unsteady 2D results can be mapped onto the 3D results. And this is where the statement of hypersonic similarity is going to be important. Before I go to the statement, I will just try to show a couple of very short videos because this is in the further discussions, we will have these wordings of blast waves, propagating waves, radial waves, and similar terminology, because that transient problem is going to be similar to that of blast waves. And actually, in real applications where we make use of it for hypersonic calculations, we are going to rely on solutions or experimental relations or experimental correlations which are available for blast waves. So because of the importance of this concept or this phenomena of blast waves, I'll try to show a couple of videos. I mean, actually, they are not very detailed ones. Very less. At least I could not get very high quality videos on that. Either they are classified or nobody has recorded it. So, but then 2-3 of them I got. Unfortunately, the middle one, the second link is not working now. So I'm trying to play the other two. Very short, but I'll try to explain what I'm trying to impress upon you by showing those videos. So when I show them, there are no, anyway, there is no audio, so we don't have to worry about it. So I'll just tell you what I want to say based on that. So for now, I'm just coming out of the slideshow, and because clicking on that link, it takes long time to, so I have kept it, I guess I had kept it somewhere. This, I guess, is the first video. Right to. I hope you are able to see that. If not, tell me. I'll rerun it. Clarity is not admittedly clarity is not very high, but then I'll try to tell what I'm trying to highlight here. Say This is a cylindrical shock wave generated by exploding wires. I've seen some article on that, but I really don't know what method they have used for it. Anyway, but then this is a cylindrical shock wave. What does it mean? A shock wave, a pressure wave, a strong pressure wave moving in the radial direction, cylindrical. So we can assume that what you see here in the as the bright region near the center, bright region near the center. That's probably is like a cylindrical. I guess they say wires, etc. So you can assume that to be a cylinder with an axis maybe parallel to the plane that we are seeing this. Okay. So and the pressure wave is advancing in the radial direction. So I'll try to play it once again. Look at that. Is the pressure wave, that shock wave, the blast wave is, and there are subsequent waves also. They are all proceeding in the radial direction. Once again, see, okay. So so if you just look at it, you know that it's a wave propagation in the radial direction, and of course it's advancing with respect to time. So it's a transient problem, right? It's in one direction. So you can consider it as one dimension because it's radially outward, and it's a transient problem. So because with respect to time, you have a variation in that. So this is a picture, or this is a visual. This is visually how it looks when you have an explosion or a blast wave being photographed, provided it's of a cylindrical source. I'll just stop this and then try running this. This is a simulation of a blast wave propagation. Apparently, it's done in Abacus. The details of simulation is not important to us, so I'll skip all these. I'll just go to I guess 120 or something. Sorry about all that. Uh, yeah, so I'm just going to 120 for 125 or something. Yeah, just look at that. That shows the simulation of pressure waves emanating from a center, that is from that corner. You can see that, yeah. Right? So they are advancing towards, from that corner, they are advancing with respect to time. Sorry. You can see that. So they are advancing with respect to time in the radial direction. It's pressure waves model, or blast waves which are modeled as pressure waves advancing in the radial direction. Okay. So in all our discussions, when we say blast waves or radial propagation of pressure waves, this kind of pressure waves is what we should keep in mind. Okay. So I am just stopping it now. And I just wanted to give you a physical feel of how these look like when we actually refer to them. So I'll go back to the presentation. Yeah. Okay. Now, so we'll come back to that. But then, what is the statement of hypersonic equivalence? I'll just read it out here first, the way that it is written, and then try to explain that. Hypersonic equivalence principle is essentially the statement that steady hypersonic flow over a slender body is equivalent to an unsteady hypersonic flow in one less spatial dimension. Okay. So steady hypersonic flow over a slender body. If I'm considering flow past a slender body, so all my assumptions regarding tau becomes important. That is d by L has to be less than 1. Okay, but I'm just saying slender body. So I have the freedom that the nose can be blunt yet. Okay, so it's a flow of over a steady hypersonic flow over a slender body for which we have seen the relations already, the governing equations. And what it says is that the principal states is that this is equivalent to unsteady hypersonic flow in one less spatial direction. Now, I just want you to look at the what I have written in letters here in using notations here. F of x, y, z, small f of x, y, z, that is 3D flow. X, y, z, but there is no time in it. So steady three-dimensional flow. This can be equivalent to x, y, t. X, y, t. T is the transient, this one. In fact, okay, x, y, t or y, z, t. So you have on one side, you have a 3D steady flow. On the other side, you have a 2D unsteady flow. And we are saying that they can be similar, or they can be equivalent. That is, one can be equivalent to the other. Now, what is the basis for saying this? Nothing but just the mathematical equivalence that we see here. These are the two equations. One for a XYZ XYZ steady flow. The other for a YZ unsteady flow. YZ unsteady, 2D unsteady and 3D steady. 2D unsteady and 3D steady. And we see that there is a mathematical equivalence between the two relations. There is a mathematical equivalence which can be observed between the two sets of governing equations. So, and one of them is applicable. The right-hand side is applicable only to hypersonic flows. So, based on this mathematical observation, we are saying that the hypersonic equivalent, we are stating the hypersonic equivalence principle that the steady hypersonic flow over a slender body is equivalent to unsteady hypersonic flow in one less spatial dimension. One less spatial. That is, if I am talking about 3D steady flow, then it should be the equivalence will be to 2D 2D unsteady flow. If I am talking about 2D steady flow, then the equivalence will be with 1D unsteady flow. So 2D steady versus 1D unsteady, or 3D steady versus 2D unsteady. Okay, subject to the assumptions of slenderness of the body. So this statement, which derives from the observation of the mathematical equivalence of the equations, is what is known as hypersonic equivalence. Now we will try to physically interpret what do we mean by this equivalence in 2D, equivalence between steady 2D and one-dimensionless in the 3D, in the unsteady domain. We will just take a couple of examples to go to that. So one, or rather, the most often quoted analogy is between the analogy of blast waves or piston-based, piston-generated waves. So the analogy between the physical situation and the physical situation for which result is available and hypersonic flow is, as we have just stated, is a relationship between unsteady flow and steady motion in one additional spatial dimension. Unsteady flow, which is, say, if unsteady flow is in n dimensions, then the correspondence is sought with steady motion in n+1 dimensions. Because unsteady motion has time as an additional dimension, so a additional spatial dimension on the other on the steady reference frame. Now, based on this analogy, so blast wave process, this is where that term we are going to use quite often is going to be introduced. They have been successfully used to estimate the pressure distribution for blunt nose bodies at hypersonic. I want you to note the second point particularly. We are going to see some examples of this, but then we will before we reach there, let's see what is the meaning implication of this statement. Based on this analogy, the analogy that we have just seen, the results of blast wave simulations or blast wave models or blast wave experimental correlations. In fact, all of these are available. Experimental studies, experimental correlations, and simulations results. They have been successfully used to estimate the pressure distribution for blunt-nosed bodies at hypersonic speeds. In fact, I should correct it as blunt-nosed slender bodies because it's only applicable for slender bodies. And so that this application or adapting those results to this is based on the analogy. And the use of is that is provide some useful trends which are in agreement with experimental data. And as we have seen already, the it is applicable only for slender configurations where the set of equations that we have seen are applicable because those equations are based on small perturbation equations. So the mathematical equivalence is only established when you consider the small perturbation theory, and that's the reason why we restrict or we have to restrict our attention to hypersonic slender bodies when we apply this principle, the equivalence principle. Okay, now coming to what we call as the any questions so far? Again, you can stop me because this is what we are talking about is somewhat convoluted because we are trying to strike a equivalence between steady and unsteady and one dimension less, etc. So if I can provide more clarification any point, I'll be happy to do that. No, okay. So we'll just please, yeah, carry on. Yeah. Hello. I'm sorry, somebody was asking something. I didn't hear properly. Okay. So I guess I'll just cover this slide also before we stop today. This is just repeating, but then trying to explain that with some sketches. The analogy that we are talking about is steady flow past a blunt-nosed body of revolution, a cylindrical body. It can be a two-dimensional slab also, we'll come to that. And also, we are talking about an instantaneous energy release on the other side. That is, when we say blast wave, it's an instantaneous energy release from a region, and it explodes in a line, in a plane that is perpendicular to the axis of motion, similar to the simulations that we have seen. So you have a radial propagation. That's a perpendicular radial propagation. So the energy that is released or that kind of propagation of a shock wave is usually what is referred to as the blast wave. So that's where we are. That's a interest that that's why we have interest in the blast wave propagation, because that is where we have the similarity. Now, if you look at the sketches on the left hand side, look at this. This is a cylindrical body with obviously slender one because the length is much higher than the diameter. So d by L is very small. A cylindrical body and has a blunt edge. You have a detached shock. Let's assume it's being considered at a hypersonic flow. Now, for a moment, you assume that you have a body standing like this, maybe in an experimental wind tunnel or something like that, and then you have flow established. Let's assume steady flow. So you are going to have a shock as indicated there. And if I look at any cross section of it, and if I project it, if you take an end view, what do I mean by any cross section? These are the cross sections. Okay, so the physical situation is I have a model, I have a slender blunt-nosed model, I have hypersonic flow past it. I assume that it will be steady. So I have a steady hypersonic flow past a model. Okay. Now, if I look from a different perspective, what it has is, if I look at different cross sections, then what I'll see on the end side is a cylindrical body in the center, a circle at the center, and as I move towards the radial direction, I will see at different pressure waves advancing in the radial direction. So when the flow is establishing, I can see that looking from the side, I can see that the pressure wave is traveling in the radial direction. Okay, so that is an in view, and remember, this is an in view, so I consider it in a particular plane, and it's just in the radial direction. So if I consider the first one as a 2D steady situation, a flow in a 2D plane under steady conditions, the advancement of it from a different perspective, when the flow is being established, I can consider it as in a radial direction, just one dimension. It's a circular, this one, but it's the advancement is only in one dimension. So a one-dimensional unsteady propagation of the wave. So a steady two-dimensional problem, I can sort of relate that to the unsteady propagation of a blast wave, a centralized wave in the radial direction. Okay, so this is the kind of equivalence that we are trying to strike between 2D, one dimension, 2D steady and 1D unsteady. This could be, actually, this is for the sake of the ease of explaining, but then similar when we say between 3D steady and 2D unsteady, this is the similar kind of equivalence that or analogy that we are going to or we are talking about striking between. Okay, so what we are saying is that study of three-dimensional steady hypersonic flow over a slender object can be considered to be equivalent to study of two-dimensional unsteady flow over the same. Study of two-dimensional unsteady flow over the same, and this is based on the simplifications that come from the slenderness approach. So the whole thing can be related to only hypersonic bodies with slenderness in the hypersonic bodies with slenderness. So what if we can do that, then steady hypersonic flow field can be, the pressure field can be constructed from an unsteady flow for a given non-pressure field in an unsteady flow in a in one less space dimension. That is, if it is 3D in 2D, if it is 2D in 1D. So in one less spatial dimension. This is the core, or this is the basis of hypersonic equivalence. We'll see the application or how this is being made use of in the next class. I'll stop here. Anything further? Any question you can ask.